Alright, welcome to our Exam 3 review for Calculus 1, Math 147. Let's go ahead and get started. First we are testing some definitions graphically here. So on the graph over here to the right we want to pick the critical numbers. Remember, critical numbers are where f prime is equal to 0 or does not exist. And so when it equals 0, you're looking for horizontal tangents, which would happen here at x equals 0. Also right here, which looks like it's about, I don't know, 1.3, 1.4. We'll allow a little bit of room for estimation there. Another horizontal tangent up here, and that's at x equals 4. And then also places where f prime does not exist. And there you're looking for a cusp on the graph, a corner. So, and I see this comes down to a point at x equals 5. So right here below that cusp at x equals 5, that would also be a critical number. Function's not defined here at x equals 1, so the derivative doesn't exist there either. But it's because it's not defined. And remember, critical numbers have to be numbers in the domain of the function. 1 is not in the domain of the function. Next, intervals where f is increasing. So increasing, it goes up from left to right. So from x is 0 to x is 1, this is going up left to right. And we can include 0, but we can't include 1 because there's not a point on the graph. And then it's increasing again from this critical number at about 1.4 up to this point, which is at x equals 4. And we can close that up on both sides. And then it's also increasing here between 5 and 6. And there is a point on the graph, so we can close that interval up. Whoops. Closed. And if I asked you decreasing, of course, then it would be 0 to 1, from 1 to 1.4, and from 4 to 5 would be decreasing down left to right. Where is the graph concave up? Curved upwards. So curved up like that. So we are concave up between -1, and it looks like we're concave up all the way to 1 there. So -1 to 1, and then remember we don't close these intervals up. And then it also looks like this guy is concave up here, so it's curved up here. It looks like it might start to curve down a little bit there, close to 1. And again, I'll leave a little bit of leeway here. But, you know, maybe from 1.2 up to, at least up to 2. Somewhere in here it starts being curved down, and in here it actually looks fairly straight. But certainly we'd know from like 1.2 up to x equals 2, it would be concave up. And you know, it might go a little bit farther. You know, it looks like it might even be concave up all the way to maybe 2.5 at the most. Concave down would be curved down, so between x is 2.5 and between x is 5, that's one interval where it's concave down. Here in this part of the graph, it's not clear that it's concave up or concave down. It looks like a straight line. Absolute maxes and mins, remember these are function values or y values. Okay, so we've got absolute min is y equals 0, and it happens at x equals 0. That's the absolute minimum point right there. So y equals 0, and that's at x equals 0. And then the absolute max, the highest point on the graph here, is right here. That's y equals 5 when x equals 6. And a local max of f, that would just be a point that's higher than points nearby. So for example, this point right here is a local maximum point. So the local max value is 4, and it's at x equals 4. So this could be y equals 4 at x equals 4. Another local maximum point would be right here. Y equals 1 at x equals -1, but this just said a local max, so we only have to give one of them. That's probably the most obvious. An interval where f prime is negative. Okay, remember that f prime less than 0 means that f is decreasing. So we want an interval where f is decreasing. So between -1 and 0, certainly the graph is decreasing. Notice that we can't include 0 because there f prime isn't less than 0. F prime is equal to 0 right here. We could also, go from 1 to 1.4, whatever this critical number is, or from 4 to 5 would be another one. Okay, and I'm just asking for an interval. You don't have to get all of them. An interval where f double prime is negative. Okay, so remember f double prime less than 0 means that your graph f is concave down. Positive concave up, negative concave down. So it looks like we're concave down in here between x is 2.5 and x is 5. But certainly from x equal 3 to x equal 5, just want an interval. Doesn't have to be the biggest interval, but 3 to 5, that would be one interval where it's concave down. And somewhere in here, that's the only place where graph is concave down. And if I'd asked f prime greater than 0, then you'd want to find where the graph's increasing instead of decreasing. Mean value theorem, you need to know the mean value theorem and also the intermediate, Rawls theorem, the mean value theorem and Rawls theorem. Mean value theorem says if you know two things. One, your function f is continuous on a closed interval AB, and 2, your function f is differentiable on the open interval AB. Then there's going to be some value c, so there is a c in the open interval AB with f prime at c, the slope of the tangent, equals the slope of the secant line. And the secant line has slope f of b minus f of a over b minus a. And part B here, we're going to verify that our function satisfies the hypothesis of the mean value theorem and then find all the values that satisfy the conclusion. Okay, so number 1, is our function f continuous? Well, f of x is a polynomial, okay, so it is continuous. Okay, it's continuous. Oops, forgot my c. Continuous on, let's see, we're looking at the interval 0, 2. On that closed interval 0, 2, because it's polynomial. Polynomials are continuous. 2, we want to check, is it differentiable? Well, let's take a derivative. If we can take a derivative, then it's differentiable. So f prime of x here is going to be equal to 3x squared minus 4, derivative negative 6 is 0. Okay, so f prime of x exists on the open interval 0, 2. Actually, it exists everywhere, but we just need it on that open interval. And then to find the values of c, we want to take and set our f prime of x, or f prime of c. Set your f prime of x, which is 3x squared minus 4, equal to our a is 0 and our b is 2. So this is going to be f of 2 minus f of 0 over 2 minus 0. So remember, if it's Rawls' theorem, then instead of f of b minus f of a over b minus a here, then the slope is equal to 0. But then you have the third condition that f of b has to equal f of a. So you'll want to look over Rawls' theorem too. Alright, so f plug in 2, that's going to be 2 cubed minus 4 times 2. So that's 8 minus 6. So this is negative 6. Minus f plug in 0, be 0, 0 minus 6. That's negative 6 minus negative 6. Over 2 minus 0 is 2. Excuse me. And that gives us a 0 on the top. Double negative here makes a positive. This is 0 over 2, which is 0. So we're trying to find when 3x squared minus 4 equals 0. So add 4 to both sides. This comes over. 3x squared is 4. Divide by 3 on both sides. X squared is 4/3. And then take square roots. And so x is going to be equal to plus or minus square root of 4/3, which is the same thing as square root of 4 on the top is 2. And then on the bottom, square root of 3 we have to leave alone. Can't do anything with that. And then we only keep the values that are inside our interval. Our interval goes from 0 to 2. Now, 2 divided by the square root of 3, root 3 is approximately 1.7. So 2 divided by 1.7, that's going to be a little bit bigger than 1, but it's not going to be as big as 2. So this is 1 point something. So it is going to be in that interval. But the negative square root of 4/3, that is negative 2 over root 3, is not going to be in there. So the only value of c that's in this interval 0, 2 is 2 over square root of 3. So that's our final answer. Number 3, we are sketching a graph. And what you want to do here is you want to do some sign charts, make some sign charts up from the conditions that they give you. You're going to have one for f prime and one for f double prime. And tell what the function's doing. So first they tell us f prime is greater than 0 on the interval negative 1 to 1, and less than 0 on negative infinity to 1, 1 to 3, and 3 to infinity. So our cutoffs here are negative 1, 1, negative 1 already got there, 1, and 3. So negative 1, 1, and 3. So negative 1, positive 1, and 3. And then we're told f prime is greater than 0 on negative 1 to 1. So it's positive in there. And it's less than 0, negative infinity to negative 1. That's here. 1 to 3 in here. And then 3 to infinity in there. So our function is decreasing, increasing, decreasing, decreasing. And next, they tell us about f double prime. F double prime is less than 0 on 0 to 3. So 0 would be right here, so that's a cutoff, and then 3 is another cutoff for f double prime. It's just the ends of the interval. And f double prime is less than 0. So f double prime is negative here, so that means concave down, like this. But then let's go up above and match here. If we are between 1 and 3, it's concave down but decreasing. If we're between 0 and 1, we go up, it's concave down but increasing. So actually, in this portion between 1 and 3, we're decreasing concave down, looks like this. here between 0 and 1, we're increasing, but concave down. Looks like that. And then over here, we're not given information about the concavity, so we can do anything we want over there as long as we have decrease, increase, decrease, decrease. And we've got this concavity between 0 and 3. We also have an asymptote. As x approaches 3 from the plus side, f of x goes up to positive infinity. And then y equals 1 is a horizontal asymptote. And then f prime at negative 1 does not exist. So here at negative 1, f prime at negative 1 doesn't exist, so that would imply that we've got a cusp there. Or a vertical tangent would be another possibility. So probably a cusp would be the easiest thing to draw. So, but first let's sketch in our asymptotes here. So as x approaches 3 from the plus, f of x goes up to positive infinity. So that means that x equals 3 is a vertical asymptote. And as you come in from the positive side, this function has to go up to positive infinity. And that agrees with this. It's decreasing after 3, so this is decreasing. Also, y equals 1 is a horizontal asymptote. So you've got a horizontal asymptote like this. So why don't we just make this guy taper off to y equals 1. Maybe we could do a better job than that. There we go. So we got our horizontal and we got our vertical asymptote. And then between 0 and 3, that's where we got to worry about concavity. So here's x equals 0, here's x equals 3. From 0 to 1, it's increasing concave down. So let's see here. Between 0 and 1, we are increasing and concave down. So increasing concave down, like that. And then between 1 and 3, we're decreasing concave down, like this. So between x equals 1 and x equals 3, we're decreasing concave down. And why don't we make that approach the asymptote that way? So that means we've got a maximum point here at 1. And that agrees with what we got here, max there, and min here. Okay, so now we agree with everything to the right of 0. To the left of 0, this thing has to be decreasing to the left of negative 1 and then increasing. So it's decreasing to the left of negative 1 right there. It's got to go down from left to right. And this is a horizontal asymptote, so why don't we have it taper off from 1 and be decreasing up until x is negative 1. We need to have a cusp at negative 1, and then it has to switch to increasing. So why don't we just make it increase and connect up with this part of the graph. So now it's also concave down here. It continues concave down, and that's okay. You know, maybe 0 is not an inflection point. It's possible. I didn't give you that information, so you got a little bit of leeway. So this is one possible graph. Not the only possible graph, but one possible graph. We got that cusp right here at negative 1, so f prime doesn't exist. Alright, we are finding vertical and horizontal asymptotes next on x over 2 minus x. Justify your asymptotes with limits and then sketch a rough graph. Alright, so vertical asymptotes, they're going to occur when denominator equals 0. So set 2 minus x equal to 0 and bring the x over as a positive. 2 equals x. So x equals 2, vertical asymptote. So we can start sketching over here. X equals 2, vertical asymptote there. And then we'll have two limits for that. We want to look at the limit as x approaches 2 from the negative side of x over 2 minus x. And then also the limit as x approaches 2 from the plus side of x over 2 minus x. Now notice if you plug 2 in, this is form number over infinity, which is going to be, number over 0, both of these. So your answer is plus or minus infinity. We just have to analyze signs. Well, this is approaching 2, but from the negative side, so x is less than 2. And so the top, x is getting close to 2, but it's less than 2, like 1.9. Well, that's going to be positive on top. 2 minus x, though? Well, 2 minus 1.9, or 2 minus 1.5, or 2 minus 1, that's always going to be positive. Or if you want to see it from the inequality down here, x is less than 2. If you bring this x over on the right as a negative, this will be the same as 0 is less than 2 minus x, which means 2 minus x is greater than 0, greater than is positive. And so positive over positive, this will be plus infinity. And then down here, x approaches 2 from the plus. That means x is greater than 2. And if we bring the x over on this side as a negative, 0 is greater than 2 minus x, which is the same as saying 2 minus x is less than 0. So you're approaching 2 on the top, which is still positive. From above, it'd be like 2.1, 2.01. Down here on the bottom, though, 2 minus 2.1, that would be negative. And here we see 2 minus x less than 0, negative. So this one's minus infinity. So as you come into 2 from the negative side, so as you come in from this side, your graph is going up to infinity. And as you come in from the positive side, come in from this side, it's going down to minus infinity. Okay, well, we need horizontal asymptote in here real quick, so let's do that, and then we'll do our sketches. So remember, for horizontal asymptote, you always look at limit as x goes to infinity or minus infinity of the function. And remember, these are the limits where you can look at dominant terms. So the dominant terms are the highest power terms. So in this case, this is going to be limit as x goes to infinity, and the only term on the top is x, and then the dominant term on the bottom is negative x. But x and x cancel, so this is just negative 1. Okay, so the function is approaching y equal negative 1. Okay, which is down here. And as x goes to negative infinity, the x's cancel out, and so you're still approaching negative 1. So we actually can change this to, x approaches infinity to plus or minus infinity, because they're both the same. Now, if the x's didn't cancel out, we might get something different than negative 1. But lots of times these guys are the same. Okay, so we've got to have the graph approaching negative 1 and approaching x equal 2. And you can stick this in your calculator if you want to. You should get something that looks like this. Again, as x approaches 2 from the minus, you're going up to plus infinity. So as you come into 2 from the minus side, you're going up to plus infinity, that direction. And as you come into 2 from the plus side, you're going down to minus infinity. So I'm going to be asymptotic to y equal negative 1. As I come into 2 here from the positive side, I'm going down to minus infinity. So there's a rough sketch. And that agrees with our limit calculations. Alright, and up next we've got the big graphing problem. So here we've got polynomial function, and you can graph this on your calculator to get an idea here, and make sure that it agrees with what the calculus is telling you. But we're finding critical numbers, increase, decrease, max, min, concave up, concave down, inflection, and then sketch our graph. Okay, so critical numbers here. There's no place where f prime does not exist, but we want to find where f prime is 0. So start doing a derivative here. It's helpful to notice, even though I didn't ask for this, that we've got all even powers here, which means we have y-axis symmetry. So that's something to keep in mind. So f prime derivative of 2x squared is 4x. Minus 4 comes down times x, decrease your exponent. Derivative of 4 is 0, and then set that equals 0. And now we got to solve this guy to find our critical numbers. So we got a common 4, and then also a common x we can factor out. So 4x comes out. Just a 1 left here. 4 and an x out there be an x squared left. So either 4x is 0, or the second piece, 1 minus x squared is 0. And in this case, bring the x squared over as a positive. 1 equals x squared. And then we take square roots on both sides. And we get x equals positive or negative 1, because we were taking the square root, positive and negative square root. So 0, 1, and negative 1. So let's get our sign chart going here for f prime. So we've got negative 1, 0, and 1 are the cutoffs there. And pick some test numbers here. Let's test negative 2, negative 1/2, positive 1/2, and 2. And I'm just trying to pick easy numbers in each region. And then we plug them back in here. I mean, you can plug back into the original, but it's easier to plug in here to tell the signs of each piece and then look at what happens to the product. So 4 times negative 2 would be negative times 1 minus negative 2 squared is 4. So 1 minus 4, that's negative. Negative times negative is positive. Put a negative 1/2 in there. 4 times negative 1/2, negative. 1 minus 1/2 squared, or negative 1/2 squared is 1/4. Because you square negative, you get a positive. 1 minus 1/4 is positive. Negative times positive, negative. Positive 1/2 in here for x. 4 times 1/2 is 2. That's positive. And then a 1/2 in here. 1 minus 1/2 squared. That's 1 minus 1/4. That's positive. Positive times positive is positive. Now plug a 2 in. 4 times 2 is 8. That's positive. And then 1 minus 4 squared, 1 minus 16, negative. Positive times negative, negative. So we are increasing, decreasing, increasing, decreasing. So we're going to have a max at negative 1, a min at 0, and then a max at 1. So let's list our intervals of increase, decrease. Okay, so f is decreasing on negative 1 to 0 and 1 to infinity. So negative 1 to 0, we can close these up because it's a polynomial. Union 1 to infinity. And it's going to be increasing on the other intervals. Negative infinity to negative 1, 0 to 1. And then our max is at 1. I'm sorry, negative 1, well, and 1. Okay, so we've got our max is going to equal the function value, the y value, f at negative 1. And then we go back to the original function for our maxes and mins and also inflection points. So 2 times negative 1 squared minus negative 1/4 plus 4. So this is going to be 2 times 1 is 2 minus 1 is 1 plus 4 is 5. And then we've also got a max at 1. And that gives us the same thing, 1 squared and 1 to the 4th, because they're even powers. So notice that f of 1, that also equals 5. So we've got a max of 5, and it occurs at two places, -1 and 1. And then our min is equal to the function value at 0, because min's at 0. So f at 0 is going to be 2 times 0 squared minus 0 to the 4th plus 4. So 2 times 0 squared minus 0 to the 4th plus 4, which is 4. So minimum of 4 at x equals 0. Alright, so now let's do f double prime. So f double prime of x. And derivative 4x is 4. Derivative of 4x cubed, 3 times 4 is 12, x squared, and set that equals 0. And let's see here, we got a 4 we can factor out, leaves a 1 here, minus 12 divided by 4 is 3x squared. Okay, 4 is never equal to 0, so it must be that 1 minus 3x squared is equal to 0. Bring the 3x squared over as a positive, so 1 is 3x squared. Divide both sides by 3. And let me switch sides with the x squared and the 1/3 here. So x squared is equal to 1/3, and then take square roots. So x is going to equal plus or minus, square root of 1 is 1, and then on the bottom square root of 3. Alright, so 1 divided by the square root of 3. So 1 over the square root of 3, that is approximately 0.57. So this is plus or minus 0.57. So now let's make our f prime chart. F double prime chart, excuse me. So here's 0. Negative 0.57 be about right here. So that's negative 1 over root 3. And positive 0.57, oh, about right here. So that's positive 1 over root 3. And pick some test numbers in each region. So remember, this is about negative 0.57, so we could pick negative 1. Between these two numbers, we could pick 0. To the right of 1 over root 3, pick 1. We're plugging back into f double prime, and we're going to tell what happens to f. So we're plugging back in here. So negative 1 goes in here. 4 minus 12 times negative 1 squared. Negative 1 squared is 1. 4 minus 12, that's negative. So this is going to be concave down. And then plug a 0 in. 4 minus 12 times 0. 4 minus 0, that's positive. So concave up. And then plug a 1 in. 4 minus 12 times 1 squared. 4 minus 12, that's negative. Concave down. And let's put these together with the increase decrease that's up above. So here we're concave down on that whole interval. But if we bring the negative 1 down here, we are concave down but increasing to the left of negative 1. So that's going to look like this. So increasing concave down there. Between negative 1 and negative 1 over root 3 in here, we are concave down. We look up, we're decreasing. So decreasing concave down would look like that. And then it switches to concave up. If we bring down our 0 cutoff here, this is decreasing but concave up in here between negative 1 over root 3 and 0. So let's extend that a little bit. Just redo it. So decreasing but concave up. So like this. Between 0 and 1 over root 3, we're concave up, but now we're increasing. So increasing concave up looks like that. And then let's bring down this cutoff at 1. between 1 over root 3 and 1, we're concave down. We look up, we're increasing. So increasing concave down looks like the left half of that guy. And then after x equal 1, we're decreasing, still concave down. Okay, so this thing looks like it's going to be upside down W. That's what it's looking like. Let's list our intervals. F is concave up on negative 1 over root 3 to 1 over root 3. And it's concave down on this interval here, negative infinity to negative 1 over root 3. And then we're going to take that and put it together with this interval here, concave down 1 over root 3 to infinity. So this would be union 1 over root 3 to infinity. And then we change from concave down to concave up here, and then from concave up to concave down here. So plus and minus 1 over root 3, we got inflection points there. So those are the x coordinates of the inflection points. We need the y coordinate. Okay, so the y coordinates, we've got to take these numbers and plug them back into our original function. So if we take f, plug in 1 over square root of 3, that'll be 2, 1 over root 3 squared. This is 2, 1 over root 3 squared, minus 1 over root 3 to the 4th. So 1 over square root of 3 to the 4th power, and then plus 4. And it's okay if you want to do a decimal here. This turns out to be approximately 4.55. And that is the same if you plug in the negative 1 over root 3. Alright, so let's get our graph going here. So I just did calculator work here. Alright, and this is y-axis, x-axis, and let's see, we've got a 1 here, and 2, negative 1, negative 2. And then our maxes here happen at 5, and our min is at 4. So we need to go up 5 units. So 1, 2, 3, 4, 5. Let's put our important points on there. So our max, when x is negative 1, y is 5. So negative 1 comma 5. When x is 1, y is 5. So that gives us 1 comma 5. Our min when x is 0, y is 4. So that gives us 0 comma 4. And then down here, our inflection point, when we input that 0.57, which is 1 over root 3, we get 4.55. So this actually gives us 0.57 comma 4.55. And then the negative also. So negative 0.57 and 4.55. Alright, so let's graph our important points. So we've got negative 1, 5, 1, 5. So negative 1, 5 right there is a maximum. Positive 1, 5, there is a maximum. 0, 4, a minimum right there. And then we've got this 0.57, 4.55. So 0.57 about here, 4.55 about right there. And then negative 0.57, 4.55 about right there. And now we're just going to transfer these pieces over here. So This is increasing concave down up to -1. So increasing concave down up to -1. Didn't do that real well. Like that. Then it's decreasing concave down between -1, -√3. So this part is decreasing concave down. Like that. Then it switches to concave up and decreasing in here. Not a real pronounced change in concavity, but a little bit. And then it's increasing concave up between 0 and √3, so that would look like this. And then it's concave down increasing between 1 over √3 and 1, like that. And then decreasing concave down after x equals 1. This is 1 and -1. And then notice we've got that y-axis symmetry. So my line's not quite going through the points. So I'll just make the points bigger. So, and helpful to label our points here. So this is -1, 5, 1, 5, 0, 4 is our min right there. And then 0.5, 4.55 right there. -0.57, 4.55 right there. And our intercepts out here where it hits the x-axis, those could be helpful too. You would set this function equal to 0, but that doesn't really factor very nicely. So, I mean, if you set x equals 0, you can get y equals 4, which is our minimum point. But if you set the f of x equals 0, you're setting this whole thing equals 0. To find the x-intercepts, set y equals 0, that's a little tougher because you're solving a 4th degree. So at that point, I would just graph on the calculator and make sure it confirms the shape of an upside down W. And I'm not going to do anything real crazy here, but I want you to understand and be able to list all of the pieces in that problem. All right, next up we have a limit and x is going to -infinity. So this means that we can look at dominant terms here. So as x gets bigger and bigger, the term that makes the difference on the top is that 2x squared. And it's underneath the square root. So root 2x squared. And then on the bottom, the highest power term is that 3x. And now we have to be a little careful here. We can break this apart on top. So this is limit x goes to -infinity. And this is root 2 and then root x squared. So product of the roots is the root of the product over 3x. And then the square root of x squared is not x, but the absolute value of x. So this is root 2 and then absolute value of x over 3 times x. And the absolute value of x, remember, is absolute x is positive x if x is greater than 0, but it's negative x if x is less than 0. And our x is approaching -infinity, so that means x is less than 0. So that's this case here. So absolute value of x then is going to be negative x. So since our x is less than 0, absolute value is always positive. That means that negative x is going to be greater than 0. So this is the limit as x goes to -infinity. And we'll have root 2 and then times negative x over 3x. And now x over x is 1. Those guys cancel. I've still got a -1 left there. So -1 times root 2 is negative root 2 and divide by 3. And let's think about this. Does this make sense? X is getting big negative. The top's underneath the square root, so it's always going to be positive. But as x gets big negative, so does 3x. So this is actually positive over negative, which is going to give us a negative answer. So if you skip this step, that's okay. If you go right to this, if you can see why you have to put a negative x in there, because you're thinking, okay, well, square root of x squared, that's got to always be positive, but our x is negative, so minus x is the positive answer. So you just got to be a little careful there. Now, if x is going to plus infinity, we don't have to worry about that. This would just be root 2 times x. Okay, we go right to this step and it'd be a positive x, but ours is negative infinity. So just be careful there. And last up, we have a max-min problem here. So let's see, we've got a box with its top that's manufactured, and the specs require the box to have a square base. Okay, I got a square base here, and it's got a top on it, and volume is 100 cubic inches. Material for the top and bottom is 3 cents per square inch, and material for the sides is 2 cents per square inch, and find the dimensions. So that's length, width, height of the box of minimum cost. So we want to minimize cost. Well, let's draw our box here first. So here's the base of the box. Well, if we sketch this box, it's going to look like this. Alright, let's try that again. And it's got a square base here. So length and width are going to be equal to each other. So why don't we call the length and width both x, and then why don't we call the height y. So that's what our box looks like. And if we were to unfold this thing, then this is asking about the cost of it, and it's cents per square inch. So that's talking about the surface area of this box. So if we laid this thing down flat and unfolded it here, this would be the bottom, the base would be x by x. And then if we took this side and folded it down, you'd have here x by y. And then this is y also, and this is y also. So the front, you fold that down, and that's base times height. So this is y. Take this side over here and fold it down. It's like that. And that's x and y. And then take the back side and flip it back down. And that is also x by y. And then the top here, take that and flip the top open, okay, and let that hang off of the back of the box right there, and that's going to be the same area as the base, x by x. So here's our top right here, here's the bottom right here, and then you've got your 4 sides. Alright, so what do we know? Well, we want to minimize cost. Okay, so we want to minimize cost, let's call that C, which is going to equal the top and bottom, and the sides have different costs. So this is going to be the cost of top and bottom plus the cost of the sides. And then for each one of those, it's going to be the area times the cost per unit area. Okay, so for the top and bottom, the area is x by x, length times width, and we've got 2 of those. One for the top, this is x by x, x squared, and then this is x by x, x squared. So this is the area, so it's 2x squared. That's the area of the top and the bottom. And then multiply it by the cost per unit area. So let's see here. Top and bottom is 3 cents per square inch. Okay, so times 3. So this is number of square inches. Length times width, they'll give square inches. And then the sides, total area of the sides, well, one side is x times y, base times height. And we've got 1, 2, 3, 4 of those. So the total area of the sides is 4xy. And then times the cost per square inch, 2 cents per inch. So that's going to be times 2. And this will be cost in cents. Okay, so this is going to be in pennies instead of dollars. So, well, let's see. We can simplify here a little bit. Again, this is number of square inches times cost per square inch. This is square inches times cost per square inch for each piece. All right, we can simplify a little bit here. 3 times 2x squared is going to be 6x squared plus 2 times 4xy, 8xy. And that's about the best we can do for right now. And then we've got to get this down to one variable. So we've got two variables, x and y. So the other relationship that we have here is that the volume is 100 cubic inches. So we also know here that our volume, which is length times width times height, so x times x is x squared times y, that equals 100. And then here it's easier for us to get rid of the y than to get rid of the x. Okay, so why don't we solve this guy for y? Divide both sides by x squared. And we get y is 100 over x squared. So let's plug that in here. So now we've got 6x squared plus 8x times 100 over x squared. And let's see, we can do a little bit of simplifying. This x here will cancel out one of these. So we've got 6x squared plus 8 times 100 would be 800. And there's just one x left down on the bottom. And now we've got a function of one variable. Now we can take a derivative, set it equal to 0, and confirm that we've got a minimum. Okay, but before we do that, let's do our interval here. Okay, so x here, remember, is the length of the base. So, that certainly can't be smaller than 0. Okay, so this is going to be 0 less than or equal to x. Actually, it would be strictly greater than 0. So x would be strictly greater than 0. And then, let's see here. X squared times y has to equal 100. X could get bigger and bigger, and as long as y got smaller and smaller, the height, that could compensate, and we'd still have a volume of 100. So there's really no upper bound on what x could be. So this would be 0 to infinity. But certainly x can't be negative. So if we get a negative critical number, got to kick that out. Alright, so this is our cost. And let's actually rewrite this with a negative exponent. It'd be a little easier to do the derivative. 6x squared plus 800 x to the negative 1. And now let's find our derivative. C prime of x then is going to be 2 times 6 is 12. X minus 1 comes down. Minus 800 times x. Subtract 1 from your exponent to the negative 2. And that's the same thing as 12x minus 800 over x squared. And let's get a common denominator between these before we set it equals 0. So common denominator is going to be x squared, right? This is 2x over 1. So this will be 2x over 1. We need to multiply by x squared over x squared minus 800 over x squared. Right, now we've got our common denominator. 2x times x squared would be 2x cubed minus 800 and then all over our LCD of x squared. Now set that equal to 0. So your critical numbers are going to be when the top is 0 and when the bottom is 0. Well, the bottom is equal to 0 at x equals 0, but we're assuming x is greater than 0. So we can ignore that critical number. But the top equals 0 when we've got 2x cubed minus 800 equals 0. And now add 800 both sides. That comes over as a positive. 2x cubed equals 800. Divide both sides by 2. X cubed will equal 400. And then take cube roots. And x is going to be the cubed root of 400. And that is approximately, let's see here. You know what? Back up the bus here for just a second. This is a 12x, and I changed to a 2x. I forgot my 1. That should be a 12. And that should be a 12. And that should be a 12x cubed. And that should be a 12x cubed. And this should be a 12x cubed. So then this won't be x cubed equals 400. It'll be 800 over 12. Sorry about that. Okay, so x cubed is going to equal 800 divided by 12, which we've got a common factor of 4 here if we wanted to. So this is 200 divided by 3, and then take cubed roots. And the cube root of 200 thirds, if you just do the calculator work there, this is approximately 4.05. So now we're ready to do our derivative test. So we do c prime above, c below. We've got a cutoff here at 0, and then we've got this cutoff at 4.05. So pick a test number here. Less than 4, let's pick 1. Greater than 4, how about 10? And plug those into c prime. And we could do c prime here or up here, either one. If we put the 1 in down here, we get 12 times 1 minus 800, which is negative. 1 squared on the bottom is positive. Negative over positive is negative. So cost is decreasing. Plug in a 10. 12 times 10 cubed. 10 cubed is 1,000, so that's 12,000 minus 800. That's positive on the top. 10 squared on the bottom is positive. Positive over positive is positive. Now cost is increasing. Yep, that's a min. Okay, so then what do they ask us? Find the dimensions of the box of minimum cost. So they don't ask us to find the minimum cost, but to find the dimensions. So this was our x, okay, and that was our base. And so it's 4.05 by 4.05, and then our y is 100 over x squared. So your y is 100 divided by x squared. So 100 over 4.05 squared. And that is approximately 6.08. And that's inches, and this is going to be inches. Okay, so we are 4.05 by 4.05 by 6.08. So they wanted dimensions there. and we gave them dimensions. Alright, and let me add one more problem on here for practice. Let's make this a number 8. The last section was Newton's method, and what we want to do is let's use Newton's method. To find x2, the second approximation to the root for f of x equals x squared plus x minus 3. And let's do this with x0 given to be 1. So this means that our first approximation, our first guess to the root for this function is 1, and we want to use the iteration formulas to find x2. So remember here that xn plus 1, the next guess is always the previous guess, xn, minus f prime at xn over f at xn. Now, wait a minute, that's f at xn over f prime. So your f prime is on the bottom. So this is the iteration formula for Newton's method. So we're given x0, that means that x1 is going to equal x0, the previous guess, minus f at x0 over f prime at x0. So in our case, our x0 is 1, so this is going to be 1 minus f at 1 over f prime at 1. So that'll be 1 minus f plug in 1, the original function, 1 squared plus 1 minus 3, so 1 plus 1 minus 3, that's 2 minus 3, negative 1 on top, f prime at 1, so f prime of x is 2x plus 1, just using the power rule there. Plug in a 1, 2 times 1 plus 1 is 3. And double negative makes a positive. This is 4/3, 1 and 1/3. Or if you want 1.3 bar, 1.33 repeating. And if you plug this into your calculator, use several digits of accuracy here. So then x2 is going to be, take the previous guess, so this is going to be our 1.3 repeating, minus f, plug in 1.3 repeating, divide by f prime, plug in 1.3 repeating. So it's going to be 1.3 repeating minus, okay, go back to our original function here, f plug in 1.333 repeating. So so 1.3 repeating squared is 1.77, and then plus the 1.3 repeating again gives you 3.11 repeating, and minus 3 gives us 0.1 repeating. So the top of the fraction is actually 0.1 bar, and then the bottom of the fraction is going to be 2 times 1.33 repeating plus 1. So that's going to be divided by, this will be 2 times 1.3 repeating is going to be 2.6666 plus 1. This is 3.6 repeating. So let's see if we do the division. Let's see. Just keying it in here. Okay, this part is actually 0.0303 repeating, and we're subtracting that from 1.33 repeating. And when I do the calculator work there, I get 1.303030 repeating. So we've done that process 2 times. We could keep on doing that process, and remember the idea is, this is the idea of iteration. If we iterate, if we keep repeating those same steps, take this answer and plug it in here, here, and here, do the function evaluation, the derivative evaluation, and then subtract it from that answer, that this number should get closer and closer to the place where this function crosses 0. And actually, if you graph that on calculator here, this is just an x squared equation, and you actually get that it crosses between 1 and 2, and that's this 1.3 here. So it actually looks something like this. And what we're doing is we're getting closer and closer to that place where it crosses. So first we started at 1, then we got to 1.3, and then the next step will get closer, and the next step after that closer yet, and it'll converge, have a limit of that root. That's what Newton's method does for us, and it does it by iteration. And this root, now granted on this one, this is one where we could actually confirm that root using quadratic formula. Okay, but the power of Newton's method is that, this could be an x to the 7th power, which is something that we couldn't do with a formula, but Newton's method will give us a numerical approximation. So, and in fact, your calculator uses an iterative process to compute a lot of the calculations in there. Not necessarily Newton's method, but a similar process, and that's one reason that the idea is important.